Okay, welcome to our last class meeting. So we've made it to the end of the semester, the end of the school year. Exciting time. I've got summer to look forward to in a week or so. Just wrapping up the last bit of chapter 8 today. And then, as I mentioned a couple of times already, final exam will be available tomorrow at 9 a.m. through Friday the 9th. You're certainly more than welcome to wait until finals week proper on Tuesday to take the final exam. But if you wanted to take it earlier, either on Friday or over the weekend, that gives you a little more flexibility. Okay, so the quote of the day today is from Charlie Munger, and since I'll let him kind of give the context, but the quote is this idea: better to add a sigma than to change a theory. So this comes from a lecture he did. I think this was like an invited talk, or I think it was maybe something like a graduation speech or something, but it's about an hour long for the whole thing, called Psychology of Human Misjudgment. I think it's actually a really good um, little YouTube video to watch. Just, certainly if you're going into finance or something like that. Charlie Munger and Warren Buffett were the folks who run. Um, yeah, the final will be 2 hours long. Yeah. Yeah, question in chat. Yeah, so Charlie and Warren, Charlie passed away maybe a year or two ago, and but they run Berkshire Hathaway, a large investment company. So if you're in finance, watching their YouTube videos and their shareholder meetings and things you know, is I think enlightening. But even if you're not interested in finance or investments, this particular talk talks about a lot of the ways that people make decisions, and I think that really plays into just about every career as well as just general life. So let me pop over to the YouTube video here, and then I'll play this couple-minute clip for you. And if you're interested, you can just search it on YouTube and find it if you're interested in watching the whole thing. Okay. So I think the audio should come through. If the audio is not coming through, let me know.
Big shot businessmen get into these waves of social proof. Do you remember some years ago when one oil company bought a fertilizer company? And every other major oil company practically ran out and bought a fertilizer company. And there was no more damn reason for all these oil companies to buy fertilizer companies, but they didn't know exactly what to do. And if Exxon was doing it, it was good enough for Mobil or vice versa. And of course, I think they're all gone now. It was a total disaster. Now let's talk about efficient market theory, a wonderful economic doctrine that had a long vogue in spite of the experience of Berkshire Hathaway. In fact, one of the economists who won, he shared a Nobel Prize. And as he looked at Berkshire Hathaway year after year, which people would throw in his face as saying maybe the market isn't quite as efficient as you think, he said, well, it's a 2 sigma event. And then he said, we were a 3 sigma event. And then he said, we were a 4 sigma event. And he finally got up to 6 sigmas. Better to add a sigma than change a theory, just because the evidence comes in differently. And of course, with this share of a Nobel Prize winning in money management himself, he sank like a stone.
Yeah, so that was Charlie's quote, better to add a sigma than change a theory. And he's talking about, more generally the idea that if we have a point of view that we're really invested in, we're going to explain away any evidence that comes in. So he was saying that this guy was part of the team that got the Nobel Prize for the efficient market hypothesis, which roughly speaking says that a company or an investment can't beat the market on average over a long period of time. So roughly speaking, that's what they said. They have all of this evidence in support of it, but people would point out Berkshire Hathaway and say, wait, well, this company has beat the market on average over a long period of time. And they like he says, they would say, oh, that's a 2 sigma event. What do they mean by that? Well, that means that, well, maybe it's about a 1 in 20 chance. Sometimes, you can go to the casino and you're not going to win on average over a long period of time, but maybe you get lucky, right? Maybe a few people go to the casino, get lucky, and walk out with more in their pockets than they came in with. But then a few more years went by and Berkshire is still doing well. And well, at that point, they bring it to them again. And it's, oh, well, now it's a 3 sigma event. Now it's a, 1 in 300 chance is about what that means. And then 1 in 4 sigma is 1 in 40,000, something like that. going all the way out to 6 sigmas is like, you know, it's probably something like, you know, this shouldn't happen in the lifetime of the universe, or, you know, one of those kind of crazy things. So that's his point, is when people are strongly invested in a certain idea, essentially, no matter what uh, evidence you present to them, they'll just, you know, come up with some way to explain it away so that they can stick to their guns. And I think that's something that we see very commonly across a lot of different fields. So something to think about. And like I said, you know, the psychology of human misjudgment talk in general, I think, has a lot of really great ideas. So if you're looking for some, you know, something to have on in the background or something while you're walking or whatever, or, you know, riding in the car, then I think that's a good lecture from Charlie. All right, so finishing up section 8.4, adding and subtracting rational expressions with unlike denominators. Let's take a look at one more example, 2 more exercises, and then jump into section 5. So that's the plan for today. Oh, let me bring my chat back up here. Okay, there we go. All right, so we have an example here, and in this case, we actually have 3 rational expressions added or subtracted. Now, how do we handle this if we have, say, 3 numerical fractions added or subtracted? Well, we just find the LCD in the same way that we did with 2 of them, but we just have 3 of them. We think of the kind of building blocks approach. I need to be able to build the denominator of fraction 1, disassemble that, build the denominator of fraction 2, disassemble that, build the denominator of fraction 3. So I take this similar approach. I have one denominator that's x plus 2, another one that's x minus 2, and a third that is x squared minus 4. I'll take each of these 3 denominators, and I'll write out their, well, basically their prime factorization. If we were doing this just with numbers, we call it a prime factorization, but we just say that when we're doing it with polynomials, we just say fully factor it. Well, x plus 2, that's already prime. That's like smallest polynomial component that we can have. We can't get something times something else to make x plus 2, at least not over the integers. So that is kind of a fundamental building block. And the same is true with x minus 2. It's not the same building block as x plus 2, even though it has, you know, a lot of similarity, but the minus means that it's a different building block. It's a different prime factor, but it's a prime factor nonetheless. So I know that my my set of Lego blocks, so to speak, has to have an x plus 2, has to have an x minus 2. Now, it doesn't necessarily also have to have an x squared minus 4. I might be able to build part or even all of the x squared minus 4 with what I have already. Now, x squared minus 4 can be factored. It's the difference of 2 squares, x squared minus 2 squared. So it is x plus 2, x minus 2. So I see if I include 2 building blocks, an x plus 2 and an x minus 2, from that set of 2 building blocks, I could build the x plus 2. I could just take out the x plus 2 and there it is. Or I could put that back and take out the x minus 2 and build the x minus 2 denominator. Or I could put that back and use both of them together to build an x squared minus 4. So this is my LCD. Now my first fraction, x over x plus 2, it has the x plus 2 building block already in the denominator. But to make up the LCD, it needs to pick up a factor of x minus 2. So I need to multiply by x minus 2 on the bottom. But then again, I don't want to change the value of the fraction, so I better multiply by that same thing on the top. We do the same with the second fraction. Five over x minus 2. Now this one has an x minus 2 in the bottom already in the denominator. To make an LCD, I need to pick up an x plus 2 factor. So I need to multiply by x plus 2 in the bottom. Again, I don't want to just multiply by x plus 2 in the denominator because that would change the value of the fraction. I've got to also multiply in the numerator. And then I didn't give myself quite enough room here. And then lastly, we have our third fraction. Oh, not a plus, a minus, minus 10x over x squared minus 4. And I still didn't give myself enough room, but I thought I moved it over enough. But 10 minus 10x over, and I'll choose to write that x squared minus 4 as x plus 2 times x minus 2, which I see is exactly the LCD already. So I actually don't need to adjust that third fraction at all. Okay. Let me bump down below here. Now I have everything over the LCD, so I can write this all over my common denominator. Of x plus 2, x minus 2. And for my first fraction, I have x times x minus 2. For my second, plus 5 times x plus 2. And then for my third fraction, minus 10x. Now my denominator is already factored. My numerator has some terms that are factored, but the overall numerator is not factored. So I want to multiply everything out, combine like terms, and then try to factor the numerator, look for any simplification, look for any common factors that can divide out. So I still have my same denominator. I'll just indicate it that way. For my first term, I have x squared, and then minus 2x. From my second term, plus 5x, plus 5 times 2 is 10, and then minus 10x over the same denominator. If I combine like terms, I have an x squared term. There's nothing for it to combine with, so it just comes down. I have 3 terms with x's in them. Minus 2 minus 10 is minus 12, plus 5 is minus 7x. And then I have one constant term, plus 10. And I actually note that x squared minus 7x plus 10, well, I can make 10 by multiplying -5 times -2, and -5 plus -2 as the -7. So it's x minus 5 times x minus 2. If I multiply this out, the first give me x squared, then I get minus 2x minus 5x is minus 7x, and then minus 5 times minus 2 is plus 10. And at this point, I'm looking to simplify. I'm looking to divide out some common factors. Maybe I'll note my restricted values, x cannot be plus or minus 2. And I can divide out my x minus 2's, giving me just x minus 5 over x plus 2 as my final answer. Any questions on that one? So there are a lot of steps, but I think between just kind of starting off by just thinking of the analogy with numerical fractions that are added together, that gets us to basically to this point here. And then at that point, we just have a rational expression we want to simplify. So the rest of the steps, multiplying out the numerator, combining like terms, factoring, finding restricted values, dividing out, that was part of just the simplifying rational expression. So it's kind of two overall ideas, getting a lowest common denominator and putting everything over that to get a single rational expression, and then simplifying that rational expression. So those are kind of the two main ideas, I think. And then each of those has, a handful of sub ideas. But I think if we kind of think in terms of that strategy, that helps us keep track of where we're going and what we should be doing next. Okay, so let's look at these two exercises, and maybe we'll take about say maybe about 9 minutes or so. Now let's say 8 minutes. I think we can do 8 minutes, and we might come back and have to wrap up just a little bit. But we'll take about 8 minutes, work through these two, and then come back and discuss the answers. Okay, it's just about 8 minutes, so I ran out of space to write and didn't want to knock the first problem off the screen, so um, I kind of stopped that one a bit short. And let's talk about the end of this first one as well. So for the first one, we have denominators of x minus 2, x, and x squared minus 2x. And we see that both the x minus 2 and the x are already prime factors. So there's nothing we can factor with those two. The x squared minus 2x can factor as x times x minus 2. We can pull the greatest common factor of x out of both of those terms. But x times x minus 2, we see that that is actually just the same two factors we already have. So our LCD is just x minus 2 times x. So we bring down our first fraction, 5x over x minus 2. That has an x minus 2 in the denominator, but it needs to pick up a factor of x. So I multiply by x in the denominator to make my LCD, but then in the numerator as well, so I don't change the value. For my second fraction, plus 9 over x, I bring that down. That denominator has an x, but it needs to pick up a factor of x minus 2 to make the LCD. So I need to multiply by x minus 2 on the top and bottom. And then my third fraction with the minus 2x plus 18 over, and then I'll just write that denominator as x times x minus 2 in its factored form. And we see that's already the LCD, so we don't need to do anything to adjust that third fraction. Now I put them all over one fraction with the LCD, x times x minus 2 in the bottom. I have 5x times x plus 9 times x minus 2, and then minus, we have a minus sign here, so that's got to come down, minus parentheses 2x plus 18. That minus applies to the entire 2x plus 18. Multiplying out, we get 5x squared plus 9x minus 18, and then minus 2x minus 18. We got to distribute the negative as well. And combining like terms, that gives me 5x squared plus 9x minus 2x is plus 7x, minus 18 is minus 36 over the denominator. Now I could try to factor 5x squared plus 7x minus 36. But I kind of, I know that really what I'm looking at, really what I'm interested in knowing is this numerator going to be x times something? Or is it going to be x minus 2 times something? That's really all I'm interested in. If this numerator, factors into whatever, 5x plus 1 times x minus 36 or something like that, that doesn't really matter to me because there's nothing more that I can divide out. It's not all that useful for me to factor it unless I end up with something that's a common factor with the denominator that I can divide out. Well, I know that it doesn't have a factor of x that can come out because the minus 36 is a constant term. So I can't pull out a greatest common factor of x. So it's not going to factor that way. I'm not going to get a common factor of x out of the top that I can divide out with the x in the denominator. What about x minus 2? I could do a little bit of trial and error here, but there's actually another trick that I can do that I wanted to kind of point out. I can say if 5x squared plus 7x minus 36, if this was equal to, say, x minus 2 times something, where this something is a polynomial in x. So it would have to be something like, 5x plus 18, I suppose, or something like that. Well, then what would I know? I would know if I set this equal to 0, then this would also have to be equal to 0. Or in other words, one solution would be x equals 2 that would make the factored form 0 if x minus 2 was a factor that came out. But that would mean that x equals 2 would be a solution. It would be an input that would yield a 0 output of the original quadratic. If I want a shortcut, if all that I'm interested in is the question, does this factor into something that's like x minus 2 times something? I can say, well, let me plug in x equals 2. If it did factor this way, that would certainly give a 0 over here because I'd have 0 times stuff. If it did factor that way, it would have to yield a 0 from this quadratic whenever I plug in x equals 2. And typically plugging in and evaluating is a much easier process than factoring. So if I plug in x equals 2 in the numerator, from the first term I get 2 squared is 4 times 5 is 20, plus 2 times 7 plus 14 is 34, minus 36 is -2, not 0. So that's a quick way to rule out a possible common factor. So in this case, I know that I'm not going to get a common factor of x out of it just by its structure. It has a constant term, so no greatest common factor of x can come out. And I know that x minus 2 is not going to end up being a factor. Maybe it factors some other way, but it's not super useful for me to know if it factors some other way because there's nothing I can really divide out. So I'll leave my final answer like this. Okay, and moving on to the second one. Here I have two denominators, x squared plus x minus 6 and 2 minus x. We note that x squared plus x minus 6 can be factored as x plus 3 times x minus 2. Now 2 minus x, we might look at it and say, oh, okay, that's a new building block. I don't see 2 minus x here or here. I might be tempted to kind of write it in the next column over, but actually 2 minus x is basically the same building block as x minus 2, right? 2 minus x is really just -1 times x minus 2. So I'm going to flip that around. I'm going to make this -1 times x minus 2, and I see that I can really get away with using the same building block for this one. So my LCD, I'll kind of leave off the -1. It doesn't really change things substantively, but it's just kind of it's just demonstrating that we can make the second denominator look like the same building block that's one of the ones we got out of the first denominator. So my LCD will just be x plus 3 times x minus 2. Okay, so my first fraction comes down, -5x minus 5 in the numerator, divided by the denominator, x plus 3x minus 2. Well, that's already the LCD. We don't need to change anything with the first fraction. Second fraction comes down, x plus 1 over, and then just so I can recognize it a little bit better, instead of writing 2 minus x, I'll write -1 times x minus 2, so that I recognize that I have this building block already. What do I need to multiply by to make the LCD? I need to multiply by x plus 3, and I do that on the top and the bottom. Now when I come along here, I put everything over the common denominator, x plus 3, x minus 2. I have -5x minus 5. This minus 1. Remember that like negative a over b equals -a over b equals a over -b. When we have a -1 factor in the denominator, we could pop it up to the numerator if we want, or we can pop it out in front. So we could either think of this as kind of changing that addition into a subtraction, or we can think of it as hitting the x plus 1 in the top, whichever way you prefer to think about it. So to get it out of the denominator so that my common denominators work more nicely together, I'll pop it up top somehow, and I end up with minus x plus 1, and then times x plus 3. Okay, so let's proceed forward then. I have -5x minus 5, and then minus, and let me just put a big brackets here. Multiply these out, I get x squared plus 3x plus 1x is plus 4x, and then plus 1 times plus 3 is plus 3. That all gets hit with that minus. So be careful with the order of operations here and the sign and distributing everything properly. Same denominator. As an aside, once we got to here, we kind of finished our LCD, combining the separate rational expressions into one rational expression. We finished that part 1. And now we're moving into kind of the part two, simplifying this single rational expression into its simplest form. Okay, so I have then negative 5x minus 5. I do note that everything in my numerator has a minus sign on it. If I distribute my minus sign here, and these first two terms have minus on them, I might actually just prefer to, well, let me rewrite this so that it's a little bit cleaner. I might prefer to just factor out a negative 1 times 5x plus 5 plus x squared plus 4x plus 3. So just factoring that negative 1 out in front at the outset makes things quite a bit more manageable, I think. And inside my brackets, I have just one x squared term. I have two x terms, plus 5x plus 4x, so plus 9x. I can combine those like terms. And then plus 5 plus 3 is plus 8. And I see pretty quickly that my numerator factors. I'm looking for two numbers that multiply to 8 that add to 9. That's got to be plus 8 and plus 1. And do I have any common factors? Nope. So this should be my final answer. So nothing more to divide out or simplify. Any questions on adding or subtracting rational expressions? So if you get stuck, I would say, even if you get stuck on an exam, write out a fairly simple numerical fraction problem, 2/3 plus 3/4 or something like that. Go through the motions, see like what procedure do you do to solve that problem, and then what's the analogous procedure for rational expressions. Okay, well then moving on to 8.5, our last topic, simplifying complex rational expressions. So what's a complex rational expression? It's where we have the quotient of rational expressions. So if I look at this denominator, for instance, 1 over x plus 3 plus 1 over x minus 3, well, this is the sum of two rational expressions. If I look at this numerator, I can select just the numerator here, x minus 2x over x plus 3. This is actually a difference of two rational expressions. Any polynomial we could write as that thing divided by 1, and 1 is just a very simple polynomial, right? So any polynomial is kind of a very simple rational expression. So I have the quotient of two rational expressions, but where the numerator rational expression and the denominator rational expression are actually themselves, say, sum or difference of rational expressions. So I kind of have a more complex strategy here. My strategy for doing something, for approaching a problem like this is going to be pretty similar, I think, to my overall strategy for, say, approaching a problem like simplify this or even this rational expression. I consider the numerator separately. I simplify it as much as I can. I consider the denominator separately. I simplify it as much as I can. I've kind of already did that from the outset here. And then once numerator and denominator are simplified individually, then I, do whatever I need to do from there. In this case, look for common factors, but maybe something a little bit more involved down here. So let's take a look at that approach. So let me come over here and let me start by looking at the numerator. I'll just call it n, which is x minus 2x over x plus 3. If I was just given this problem and told simplify this expression, well, I would do it similar to how I approach these ones up here. I really think of this first x like being an x over 1. And this is actually a pretty simple LCD to find. The lowest common denominator is just going to be x plus 3. I just need to multiply my first term here, x, by x plus 3 over x plus 3. And then I have minus 2x over x plus 3, or I end up with x times x plus 3 minus 2x, all divided by x plus 3. I can multiply at the numerator of the numerator of this expression here, and I get x squared, and then plus 3x minus 2x is plus x over x plus 3. Now I do notice that this rational expression I end up with, x squared plus x over x plus 3, I can factor that numerator now, x times x plus 1 over x plus 3. That makes it a little bit simpler. And this is about the best I can do. I can't really divide anything else out from here. So this is my simplified form of the numerator. So this bit here is the numerator. And let's do the same thing with the denominator. So my denominator is 1 over x plus 3 plus 1 over x minus 3. So that's my denominator. And I look at this, and again, it's pretty straightforward to see what the LCD is. X plus 3 is just a fundamental building block. It's a prime factor, as is x minus 3, and there are two different prime factors. So I have the x plus 3 in the first term, but I need to pick up a factor of x minus 3. And I put that on the top and bottom. And similarly for the second term, 1 over x minus 3, I have an x minus 3 on the bottom. I need to pick up a factor of x plus 3 to get the LCD. I better put it on top as well so I don't change the value of the fraction. And there we go. I could put all of this over the common denominator, x plus 3 times x minus 3. From my first term, I have 1 times x minus 3 is just x minus 3 plus 1 times x plus 3 is x plus 3. I actually see the plus 3 and the minus 3 go away. And I just end up with what? 2x over x plus 3 times x minus 3. That is what my denominator turns out to be. Okay, so I did this kind of to the side, like scratch work. But now I can come back and I notice that my rational expression is like numerator over denominator. It's really numerator divided by denominator, right? Or it's really numerator is x times x plus 1 over x plus 3. That was the numerator. And then divided by the denominator, what did that simplify down to? 2x over x plus 3 times x minus 3. Well, at this point, I just have the quotient or the division of two rational expressions. This was one of the earlier things we talked about in the chapter, is how to divide or multiply, but relevant here is divide two rational expressions. Well, I take the one after the divided by sign, I flip it and I multiply. So that was the same property from numerical fractions. If I have numerical fraction divided by numerical fraction, I invert and multiply or flip and multiply. Do the same thing here. The divided by turns into a times, and I invert, I switch my numerator and denominator, but just for the one after the divided by sign. Now I know that if I'm multiplying fractions together, I just multiply across the top, multiply across the bottom. Nicely enough, I've already done all the legwork of factoring everything. And now I see my x plus 3's divide out, my factors of x divide out. And what am I left with? X plus 1 times x minus 3 on top, divided by, well, just the number 2 on the bottom. So that is all. Okay, so that was one approach. We might be able to make things a little more efficient. Let's actually, let me just copy this down. So that was kind of the, I guess you could call it like sledgehammer approach. It definitely works. Can I make things a little more efficient? One thing I could do is I could look at all the denominators across the whole problem. I have an x plus 3, I have an x minus 3, and that's it. My LCD, my lowest common divisor, or we might call it like a least common multiple here. Sorry, lowest common denominator, or we might call it least common multiple, is going to be x plus 3, x minus 3. One thing I could actually do is actually just multiply the entire numerator and the entire denominator by this x plus 3, x minus 3. Now this does get, oh, you have to be a little careful with the order of operations here and make sure that everything distributes properly. But you could do this. So let's look at what are the costs and what are the benefits of doing something like this. The benefit is that a lot of stuff goes away really quickly. So if I look at my overall numerator, so speaking about all of this stuff up here multiplied together, what do I end up with? Well, I end up with x times x plus 3 times x minus 3, and then minus 2x. But I noticed that the way that I constructed this x plus 3 in the bottom here will divide out with this x plus 3 when I multiply through. So in that second term, the x plus 3's will go away, and I'll just be left with x minus 3. Now we might be a little bit scared because we look at this and we think, oh, if I multiply that out, that's going to be a cubic. And cubics are really difficult to factor. But I do have this greatest common factor of x minus 3 that I can pull out first. That kind of helps us out quite a bit. And if I look at the denominator, maybe I'll use blue for this one. This whole denominator, right, this bit has to distribute into those two terms. So x plus 3 times x minus 3 over x plus 3 just gives me x minus 3, plus x plus 3 times x minus 3 over x minus 3 gives me x plus 3. So what's the benefit? Oh, drop my pen. What's the benefit of doing this? I get a lot of massive cancellation very early on. What are the costs? Well, in terms of complexity, I happen to have kind of similar similar denominators in the numerator and denominator overall here. So that made my LCD easy to find, but if I was dealing with 4 denominators instead of 2, up here I get to deal with, 2 denominators up here and 2 denominators down here. But if I had to deal with 4 all at once, that increases complexity. Also, using the distributive property here, we have to be very careful to distribute everything properly. So this gets distributed to both of those terms in the numerator, as well as in the denominator. But we see the benefit is that basically in one line, I end up with something that's much nicer and simpler to work with, right? Rather than having to do 3 or 4 or 5 lines of work to simplify the numerator down to still not a very nice rational expression. Same with the denominator, and then several more lines to do all the cancellation. We're kind of doing all the cancellation up front. We're reducing the complexity up front before we increase the complexity again. Up here, we kind of, in a sense, like increase the complexity like 2 or 3 times at the beginning before trying to come down the other side of that mountain. But, again, the downside here is there are other forms of complexity that we're sacrificing. We have to deal with more denominators. We have to deal with more distributive properties that we make sure that we get just right. Okay. Or wrapping it up, here we would have in the numerator, again, important to factor out this x minus 3 before we start multiplying everything out, or it's going to turn into a mess pretty quickly. And then what am I left with? X squared plus 3x. And then minus 2x over, and x plus 3 plus x minus, or sorry, x minus 3 plus x plus 3 is 2x. So this gives me x minus 3 times x squared plus 3x minus 2x is x squared plus x, or that's x plus 1 times x over 2 times x. My x's go away, and I get the same x minus 3, x plus 1 over 2 that I got before, but in only a couple of lines of work instead of, a few lines here, a few lines there, and then another few lines over here. Each individual step, I think, is more obvious. The kind of overall strategy is more obvious. Doing it this kind of like sledgehammer approach, you're just chipping away at the problem little by little. But I think the more elegant solution is to do something like this. But you see that both of them get you the correct answer in the end. If you understand what we did here with kind of getting the kind of in quotes LCD, the overall least common multiple for all the denominators in the problem, in the overall numerator and in the overall denominator, finding all the denominators, getting this LCD type thing, multiplying by it. It's a little bit like when we have linear equations and we clear fractions at the beginning, right? If I have like 1/2 x plus 1/3 equals 2x minus whatever, 2/3 or something. I would look at all the denominators, 2 and 3, I find an LCD of 6, and I multiply both sides by 6. Right, and then when I distribute, I get 3x plus 2 equals 12x minus 4. It's a similar idea to that, where I'm kind of clearing as many denominators as I can in one step here, and then dealing with hopefully what it ends up being a simpler rational expression to deal with from that point forward for the simplification step. Okay, so 2 approaches. Either one gets you the right answer in the end. One of them is a little more efficient than the other one, but also requires a little more in-depth understanding of the strategy. And the first one here, if you're not sure what to do, you can just kind of start chipping away at it, right? Down here, if you're not sure what to do, it's like, well, it's hard to kind of work out why you should do this thing. Why should I, take all of the denominators in the whole problem and find the least common multiple? Okay, so let's look at one exercise So simplify this complex rational expression. In the numerator, we have 7 plus 2 over q minus 2. And in the denominator, we have 1 over q plus 2. So maybe take about, maybe 3 minutes for this one. This one should go pretty quickly. It's not as complex as the last one. So take about 3 minutes for this one, and we'll discuss the answer. Okay, it's about 3 minutes or so. So let's take a look at this one. We see the denominator is actually pretty simple already. The denominator, 1 over q plus 2, is already a fully simplified rational expression. So our focus is really on the numerator here. 7 plus 2 over q minus 2. We see pretty clearly we're going to have an LCD of q minus 2. So we think of that 7 as like a 7 over 1. We multiply by q minus 2 on the bottom to make a denominator q minus 2, but also on the top as well, so we don't change the value of the fraction. We can put this over a single fraction now. We can put it in a single rational expression with q minus 2 in the denominator. In the numerator, we have 7 times parentheses q minus 2, and then plus 2. Multiplying out gives me 7q minus 14 plus 2, or 7q minus 12 in the numerator, divided by q minus 2. Okay, so my overall numerator turns out to be 7q minus 12 all over q minus 2. Now coming back to my original problem, I see that I have numerator divided by denominator, or I can think of that as like numerator divided by sign, followed by denominator. Or that is 7q minus 12 over q minus 2, the numerator from over here, divided by my denominator. What's my denominator? 1 over q plus 2. I have now the quotient of two rational expressions. How do I handle this? Well, I take the rational expression that's after the divided by sign, I invert and I multiply. So I swap numerator and denominator, flip the fraction, I get q plus 2 over 1, and that's multiplied on now. I multiply those together, I get 7q minus 12 times q plus 2. Be careful that it's the entire 7q minus 12 multiplied by the entire q plus 2, and then divided by q minus 2. Now, everything is factored already in the numerator and denominator. Do I have any common factors? Again, it might be tempting to think that q plus 2 and q minus 2 are like common factors or close to common factors, or maybe like divide out and make a minus 1 or something, but that's not the case. Q plus 2 and q minus 2 are like different fundamental building blocks. They're different factors. Even if I thought I could pull out a minus 1 here and get minus 1 times 2 minus q, I still don't get a plus connecting the two. So these are not common factors. Be a little careful about that. It can be an easy mistake to make, but this is the simplest we can get. And of course, the 7q minus 12, I don't think I explicitly said it, but nothing factors out of there. The only thing that could factor out is maybe a numerical common factor, but between 7 and 12, they don't share any common factors. But if this was like, if it ended up being 6q minus 12, we could factor out a factor of 6. Okay, let's look at this one here, this example. Simplify this complex rational expression. We have a numerator, an overall numerator that's 3 over m plus 3 over n. And we have an overall denominator that's 1 over m squared minus 1 over n squared. When we have like fractions over fractions like this, sometimes it can be hard to parse what's going on, but it makes it clear that this is the overall numerator and this is the overall denominator, because we have this bigger fraction bar in the middle here. As a little side note, one thing that really irks me with mathematical typesetting is if we had like, 3 over m over 1 over n squared, it's like, I know what they're trying to say there, but sometimes this middle bar will only be like a smidge wider than the top or bottom bars, and then it's actually really hard to tell what's being communicated. It's a little bit like if somebody was speaking valid words, but they were kind of like mumbling along, you like kind of can't understand it. If the typesetting is funky, it can make it hard to understand sometimes. But here, because we have the sum in the numerator and the difference in the denominator, it makes it very clear. So just a little side note, if I was writing a problem like this, I would put parentheses here and parentheses there. They're not strictly needed from a mathematical standpoint, but the typesetting is such that this makes it much clearer what I'm saying to the recipient. There's a non-trivial amount of mathematics that is notation and typesetting, and the way that we present things. The way that we present things is sometimes as important, or maybe even more important than what we're presenting, especially when there's no context going into it, right? It's not like we did a big physics calculation and came out with this and we know exactly where this came from. In this case, in the examples we're doing here, these are isolated examples. So if you ever see those like things that go around on on the internet all the time, it's like, what is 6 divided by 3 times 2 plus 1 or something like that, and it's like, well, do you do the 6 divided by 3 first, or do you do the like 3 times 2 plus 1 first? Or in my mind, it's like, okay, this isn't so much arguing mathematics as it's arguing linguistics. It's arguing the way that's communicated. And if there's this much disagreement in what this means, that means that the person who wrote it down maybe could have communicated it better. So little tangent there, I guess, but anyway, so it is clear here though that this is the numerator, this is the denominator, and let's start with that. So we have our numerator here, I'll call it capital N. We'll start by simplifying it. 3 over m plus 3 over n. And we see our denominators are m and n. These are just both individual building blocks. You really can't get any simpler than these. So my LCD has to just be m times n. So I look at 3 over m. That has an m building block in the denominator. It needs to pick up an n building block. So we multiply by that in the denominator. And again, we don't want to change the value of the fraction, so we multiply in the numerator as well. So net, we're only multiplying by 1. And then our plus 3 over n, that has an n building block, needs to pick up an m building block, and in the numerator as well. Or I see that this is 3n plus 3m over n times m, or m times n. This is what my numerator ends up turning out as. What about my denominator? Maybe I'll do the denominator in black here. My denominator, 1 over m squared minus 1 over n squared. Well, again, I see that my one denominator just has kind of 2 of the m building block, and the other denominator has 2 of the n building block. My LCD is m squared times n squared. My first fraction, 1 over m squared, has my 2 m building blocks, but it needs to pick up 2 n building blocks. And if I multiply by that on the bottom, I better multiply by it on the top as well. Okay, and then similarly, I have 1 over n squared for my second fraction. I've got the 2 n building blocks taken care of. I need 2 m building blocks as well to make the LCD. So I multiply by m squared on the top and bottom. Or this is n squared minus m squared over m squared times n squared. This is the denominator. Now, I actually see in both of these cases, I can simplify a little bit more. I think that's going to be fruitful here. So let me go ahead and do that. I can factor out a common factor of 3 here. And down here, I actually recognize n squared minus m squared as a difference of 2 squares. So this is going to be n plus m times n minus m. Okay, now coming back to my original problem. I need to figure out what is numerator divided by denominator, or what is 3 times n plus m over n times m, that rational expression divided by n plus m. Oh, I'm running out of space here. N minus m over m squared n squared. I have a quotient of 2 rational expressions. I'm dividing them. So I take the one being divided by the one at the end after the division sign. I invert and multiply. So I'm just rewriting everything except flipping that second fraction. And now I know that when I multiply these together, I'm really just kind of, in essence, extending this division line across here. And I see I get some nice cancellation. N plus M divides out. And I also divide out one factor each of M and N. So what's left in the numerator is 3mn, and in the denominator, n minus m. There's nothing more that I can divide out here. I've accounted for all of the bits that were left over. So this looks good. This is going to be the final answer. So this is the final answer that I boxed these two intermediate final answers. So I'll give that one a double box. So that's the final answer. Now we could have taken the shortcut method here. Actually, I'm just going to pop it down here. We could have alternatively taken the shortcut method here. We could have recognized that my denominators are m, n, m squared, and n squared. So my LCD is going to be m squared times n squared. I need two m building blocks and two n building blocks to make to be able to make any of these four denominators. And then I multiply numerator and denominator by that. So I take this thing, multiply by m squared n squared, and same on the bottom. Now, if I multiply through by m squared n squared, the 3 over m, I get 3m n squared. The 3 over n multiplied onto that gives me plus 3m squared n. Then divided by, when I multiply by m squared n squared, the m squareds go away, and I get n squared from the first term, and then minus m squared. The n squareds go away, and I get minus m squared in the second term. Okay. Or again, I see I get n minus m, n plus m in the bottom. I see I have a greatest common factor of 3m n times, and in the first term I'm left with an n, and the second term I'm left with an m. These divide out. I get my 3m n over n minus m. Same answer as up above. Quite a few fewer steps, but the overall strategy might be a little bit deeper. Why did I come up with this? Why did I take this approach? It is faster. Basically, what we're doing is all of this cancellation that ends up happening, we're doing a lot of that cancellation up front. So we're doing that cancellation, and that results in us clearing the fractions. So we really only have to deal with one rational expression. But again, that's maybe a slightly more advanced technique. If you saw that and you wanted to take that approach, you're certainly welcome to. But if you want to just take the kind of more straightforward approach, that's perfectly fine too. Okay, and one last exercise. Simplify this complex rational expression. In the numerator, we have 2 over r minus 9. In the denominator, 1 over r plus 9 plus 3 over r squared minus 81. So take a crack at this one. We'll take maybe about 4 minutes or so for this one. Come back and discuss the answer. Okay, it's just about 4 minutes, so let's look at this one. So here we have numerator over denominator again. We actually see the numerator is pretty darn simple already. So 2 over r minus 9, not much we can do to simplify that. So we'll focus on the denominator. 1 over r plus 9 plus 3 over r squared minus 81. I notice the r squared minus 81 denominator factors into r minus 9 times r plus 9. And that's going to be my LCD because the other denominator has an r plus 9 building block in it already. I just need to multiply by r minus 9 and the other one on the top and bottom. So doing that, I put everything over the common denominator. I have 1 times r minus 9 and then plus 3. So just r minus 9 plus 3 in the numerator over that common denominator of r plus 9, r minus 9. And the r minus 9 plus 3 turns into an r minus 6, and that's our denominator. So coming back to our overall problem, we see that we can think of that as numerator divided by denominator, or as 2 over r minus 9, that's the numerator from up here, divided by this simplified form of the denominator, r minus 6 over r plus 9, r minus 9. And now we have a rational expression after the divided by symbol, we invert and multiply. We make this r plus 9 times r minus 9 over r minus 6, all multiplied on. We can multiply the numerators, multiply the denominators, get 2 times r plus 9 times r minus 9, all over r minus 9 times r minus 6. And we do see that the r minus 9 factors divide out. Nothing else really divides out or simplifies. So I'm left with 2 times r plus 9, all over r minus 6 as the final answer. Okay, any questions on chapter 8 on rational expressions, on anything we talked about? All right, so just a reminder, final exam will be available from 9 a.m. tomorrow through 11:59 p.m. on Friday the 9th. So a week from tomorrow. You're certainly free to take it during final exam week, but make sure that you don't wait until the last minute or the last day to take the exam. Strongly recommend planning to take it on or before Wednesday night. And then if anything happens, like for instance, the crazy weather we had that knocked out some people's power and internet connection and so on, there's time to figure out an alternative. If something like that happens on, say, Wednesday, if you wait until Friday at 8 p.m. when it's due at 11:59 p.m. and then something knocks out your power, it's a lot harder to find an alternative at that point. So strongly recommend planning to take it a bit early. You can still be in finals week, Tuesday or Wednesday, something like that, but don't wait until Friday to take the exam. All right. So answer to what somebody posted in chat is yes. Yes, so that is entered in already. Yep. Yeah, so I hope it's been a good semester for you and a good class. I hope that the rest of your classes and final exams and projects and all of that are kind of going well. I'll have office hours this afternoon this morning from 10:30 to 11. I do have to cancel my office hours tomorrow. I'll post about that this afternoon. I have a meeting that came up, so I won't be able to hold office hours tomorrow, but I will have office hours on Monday. Or if anybody has any questions, you can always email me or reach out that way, and I'm happy to answer any questions you have. But yeah, I hope it's been a good semester for everybody, and I hope the next week or so goes well, and then that you enjoy your summer. So have a good one. I'll see you all.